let's kind of go into a little bit more detail of each one of these four groups. The first group that we're going to look at are linkage isomers. And I'll give you an example of a complex, and we can look at the two isomers that form from this particular complex. So if we have cobalt as our central transition metal cation, and then we have NH3, and we have 5 different ligands around that central transition metal cation, then we also have NO2, and we can put brackets around this complex, and the overall complex has a 2+ charge. So here we have cobalt in the center. It's surrounded by 5 ammonias and 1 NO2. So its overall coordination number is going to be 6, and this tells us that we have an octahedral complex ion. So when we draw this octahedron, we have cobalt in the center, and there's going to be 6 different bonds to that cobalt central atom. 5 of them are going to be NH3, and 1 of them is going to be NO2. So I'm going to draw the 5 NH3s around here, and in each case, the nitrogen is going to coordinate, the nitrogen from the ammonia is going to coordinate to the transition metal center. That's going to happen every time for ammonia. NO2 is something, is a little bit different, because in the NO2, we can have, in one case, we can have the nitrogen bind to the transition metal, and that means if we draw the Lewis structure out, we have a single bond to oxygen and a double bond to oxygen that's going to look like this. I'm going to circle the nitrogen, indicating that this is the atom that will bind to the cobalt transition metal center. What we find in another case is if we compare this particular complex to the same complex with the same ligands, we can get a different atom that binds to that cobalt transition metal center. In each case, we're going to have 5 ammonias coordinated to our cobalt center. So again, when we draw these 5 ammonia groups around here, the molecule to the, or the complex ion to the left and the complex ion to the right is exactly the same. The thing that could potentially change here is how the oxygen is coordinated to this particular transition metal complex, or how the NO2 group is. Because the NO2 group can have an oxygen coordinate to a nitrogen and then have a double bond over here to this oxygen. I'm going to circle the oxygen here because that is the atom on the ligand that is directly bound to the transition metal center. The physical property that's different here is this complex over here on the left is a yellow-orange color. The complex over on the right is a red color. So just how it's the same thing in terms of when we saw a different color for cis and trans isomers, in this case, we see a different case for linkage isomers. And we have to give a particular name then for this linkage isomer. If the linkage isomer is bound, in this case the NO2, directly bound to the nitrogen, we call this the nitro ligand. And if it's bound directly to the oxygen, we call this nitrito. And we're going to find either on Wednesday or Friday that the nomenclature for these transition metal complexes can get a little crazy. Okay? But we have to come up with a name in place that distinguishes between these two particular isomers. Because in each case, the bond to the transition metal is different. We have the same ligand. In case number 1 down here, the bond is directly through a nitrogen. In the case over here on the right, the bond to the cobalt is through an oxygen. so we have the same exact complex, but we have different bonding environments around here. And as a consequence, we have different colors. In terms of linkage isomers, examples of common ligands are NO2, and also we have SCN minus. So in each case, for the NO2, and sometimes I should probably write this out as either ONO, and we can sometimes distinguish which atom is then bound to that transition metal center. Okay? And I'll emphasize again that in a linkage isomer, you have different bonds to the transition metal center, so that fits under the structural isomer category.